Assalamu alaikum students. Welcome to lecture number 12 of CS 317 operating systems. This video covers the topic of concurrency. We use chapter number 5 of the William Stallings book. In the last lecture, we were introduced to the concept of concurrency. Concurrency is the overlapping of lifespans of different events. We realize that sometimes concurrency is desirable and sometimes it is problematic. We realize that concurrency related problems always exist for shared modifiable data. So if we have data that is not shared, just local, then we will not have any concurrency problem for it. If we have data that is read only, it cannot be written to, then we will not have any concurrency related problem to it. For a concurrency related problem to appear, the data has to have both properties. It should be shared and it should be modifiable. We realized what race condition is. We were introduced to the types of process interaction. We continue discussion on the subtopic process interaction. We can classify the ways in which processes interact based on the degree to which they are aware of each other's existence. Sometimes processes are totally unaware of each other. This is one kind of interaction. Sometimes processes are indirectly aware of each other. So this is the second kind of interaction. And the final kind of interaction is when processes are directly aware of each other. I have added this slide to help you remember where we ended our last lecture. We had discussed that the first kind of processes, which are unaware of each other, are in a competition. What are the problems of competing processes? We face three control problems: mutual exclusion, deadlock, and starvation. The last two problems are a consequence of the first. What I mean to say is mutual exclusion leads to deadlock and starvation. Now let us understand them one by one. Mutual exclusion. When two or more processes require access to a non-shareable resource, one of them is given access while all the others are made to wait. As long as a process uses the resource, access to the resource is not granted to anyone else. This discipline is referred to as mutual exclusion or ME. The resource on which this discipline is enforced is called a critical resource. The lines of code that use a critical resource are collectively called the critical section of the process. It is important that only one program at a time be allowed in its critical section. Suppose two or more processes require access to a printer. During execution, each process will be sending commands to the I/O device, receiving status information, and sending data. We do not want two processes to have control of the printer at the same time. Otherwise, lines from both processes will be interleaved and we will get a useless printout containing bits and pieces of two different printouts. On this slide, we look at code to implement mutual exclusion. There are n processes and they share a resource RA. The yellow box shows the lines of code of each process that use RA. This is the critical section of each process. There are two functions, enter critical and exit critical. Each function takes as an argument the name of the shared modifiable resource that all the processes want. The enter critical function lets only one of the processes calling it to move to the next line of code after it. In other words, enter critical allows one process to move into the critical section. All the others are made to wait. When a process calls exit critical function, a signal is sent to enter critical to let one process move to the next line of code. So the departure of a process from the critical section enables the entry of a waiting process into the critical section. Deadlock. Consider two processes P1 and P2 and two resources R1 and R2. Suppose that each process needs access to both resources to perform its function. A process leaves an allocated resource only when it has finished its work. The operating system assigns R1 to P2 and R2 to P1. Each process is waiting for one of the two resources. P1 is waiting for R1 and P2 is waiting for R2. Neither will release the resource that it already owns until it has acquired the other resource and performed its task. The two processes are deadlocked. You ask your sibling to make you a cup of tea. Your sibling asks you to go and buy a bag of chips. You say you will go to buy the bag of chips after you have had tea. Your sibling says he or she will make you a cup of tea after you have bought the bag of chips. This is a deadlock. Neither of you will be able to get what they want. A deadlock is a circle of want. It can also be called a circle of wait. A wants something B has. B wants something C has. C wants something D has. D wants something A has. Look at it again. A waits for B. B waits for C. C waits for D. D waits for A. Starvation. Suppose that three processes P1, P2 and P3 each require periodic access to resource R. The OS grants R to P1 and both P2 and P3 are waiting. When P1 exits its critical section, it relinquishes R. Either P2 or P3 should be allowed access to R. The OS grants access to P3. Before P3 comes out of critical section, P1 again asks for access to R. The OS grants access to P1 after P3 has finished. Before P1 comes out of critical section, P3 again asks for access to R. The system keeps alternating between points 5 and 6. R goes to P1, P2 and P3 wait. P1 leaves R, R goes to P3, P1 and P2 wait. P3 leaves R, R goes to P1 and so on. P2 may be denied access to the resource indefinitely. So we say that P2 is starving. Pause the video and try to furnish the answer to this question. What is the difference between starvation and deadlock? We have been talking about processes that are not aware of each other. Now let's talk about processes that are not necessarily aware of each other by their respective process IDs, but they share access to some object. For example, multiple processes having access to shared variables or shared files or databases, processes reading from and writing to an IO buffer. By the way, an IO buffer is a set of memory locations reserved for an IO device. Anything written into the buffer is transferred to the device by the device driver. So if you want to store data on a device, you must write the data in its IO buffer. The device driver fetches data requested by a process from the device and writes it in the buffer. So if you ask the device for data, you will find it in its IO buffer. Such processes exhibit cooperation by sharing the common object. Cooperation by sharing. Processes may use and update the shared data without reference to other processes, but know that other processes may have access to the same data. They do not know who they are sharing a resource with. They only know that they are sharing a resource. They know that the variable they are using is global or the file they are using is a shared file. The control mechanisms must ensure the integrity of the shared data. Data integrity is the overall accuracy, completeness, and consistency of data. It refers to the trustworthiness of data. Data has integrity when it is correct from the time of its creation to the time of its deletion. But if during this time there are chances that data may have become invalid or incorrect, then we say that data has lost its integrity. For example, you have stored your friends' names and phone numbers in Google Contacts. Let us suppose that Google undergoes an update and later when you dial a friend's number, an unknown person responds. Actually, during the update, contact information in your list got corrupted. Now that you know what happened, can you dial a friend's number with confidence? Are you afraid that you will ring into some unknown person again? You still have all your contacts. However, you do not trust them. So we say that your contacts have lost their integrity. In the case of processes cooperating by sharing, we face four control problems: mutual exclusion, deadlock, starvation, and data coherence. Data can be used two ways. It can be read or written. Mutual exclusion only needs to be enforced when the shared resource is being written to. If two or more processes are reading a shared buffer, they can do this simultaneously. This is because they are not changing the contents of the buffer. They are only reading it. Data coherence. Data that is coherent is data that is the same across the network. Data that is coherent is data that is the same in all places where it is stored. If there are more than one copies of data, all contain the same value. Consider an application in which various data items may be updated. Suppose two items of data, A and B, are to be maintained in the relationship that A is equal to B. That is, any program that updates one value must also update the other to maintain this relationship. Two processes P1 and P2 contain code shown in box number 1. If the state is initially consistent, each process executing separately will leave the shared data in a consistent state. Now consider the following concurrent execution sequence in which P1 and P2 execute instructions according to the sequence in box number 2. They use A and B following mutual exclusion discipline. That is, only one process accesses each variable at a time. While P1 updates A, P2 updates B. Then while P1 updates B, P2 updates A. We start with A equals B equals 1. P1 executes its first instruction and A is incremented to 2. P2 executes its first instruction and B becomes 2. P1 executes its second instruction and B is incremented to 3. Finally, P2 executes its second instruction and A becomes 4. We have A equals to 4 and B equal to 3. At the end of this execution sequence, the condition A equals B no longer holds. The two variables have lost coherence. The problem can be avoided by declaring the entire sequence in each process to be a critical section. Instead of enforcing mutual exclusion separately on both variables, we enforce mutual exclusion on the code of each process that manipulates any of the two shared variables. The two red boxes indicate the critical sections of the processes. Thus, we see that the concept of critical section is important in the case of cooperation by sharing. XYZ is the name of the file which holds the two shared variables A and B. When many processes call enter critical for file XYZ, one of them is allowed to move on to the next line of code or its critical section. The others wait. The process in the critical section executes both instructions mandatorily. Since both variables are updated together, they remain coherent no matter which process executes first. When a process calls exit critical, a signal is sent to enter critical to allow one waiting process to move on to the next line of code or its critical section. Processes directly aware of each other. These are processes that can communicate with each other by process ID and that are designed to work jointly on some activity. For example, a process spawns a child. The parent process asks the child process to do a particular task. Both processes know each other and communicate with each other. Such processes exhibit cooperation by communication. For example, you and your friend are assigned a group project for operating systems. You know each other's names, phone numbers, and email addresses. You regularly talk with each other and email each other to compile the project report. In the case of competition, processes are sharing resources without being aware of the other processes. In the case of cooperation by sharing, processes are sharing values. And although each process is not explicitly aware of the other process, it is aware that the data or file it is working on is global or shared. When processes cooperate by communication, they participate in a common effort. The communication provides a way to synchronize or coordinate or order the various activities. Communication consists of messages of some sort. Functions for sending and receiving messages are provided by programming language or the operating system kernel. In the case of processes cooperating by communication, we face two control problems. Deadlock. P1 will run when it gets message from P2. P2 will run when it gets a message from P3. P3 will run when it gets a message from P1. So again we see a circle of wait here. This is a deadlock. Starvation. I have an example for you on the next slide. Because nothing is shared between processes in the act of passing messages, mutual exclusion is not a control requirement here. The processes do not use shared or global data. They make a message and pass that message to the other process. You and your friend are writing your thoughts to each other on a whiteboard. The whiteboard is a shared space. In another scenario, you write a letter, then you send it to your friend. So when the letter is with you, it is not with your friend. And when it is with your friend, it is no longer with you. Now I will give you that example of starvation that I promised. Suppose you have three processes, P1, P2, and P3. P1 periodically sends a message to either P2 or P3. When any one of P2 or P3 receives a message from P1, it executes some code. As long as P2 and P3 do not receive a message from P1, they wait. P1 sends a message to P2. P2 executes its code. P1 again selects P2 and sends a message to P2. P2 executes its code again. P1 again selects P2 and sends a message to P2. P2 executes its code again. P3 is waiting for a message from P1. There is no deadlock because P1 remains active, but P3 is starved. This table brings all the kinds of process interaction in one place. Conditions are not always as clear-cut as suggested in this table. Several processes may exhibit aspects of both competition and cooperation. Requirements for mutual exclusion. Any facility or capability that is to provide support for mutual exclusion should meet the following requirements. Number 1. Mutual exclusion must be enforced. Only one process at a time is allowed into its critical section among all processes that have critical sections for the same resource or shared object. Number 2. A process that halts in its non-critical section must do so without interfering with other processes. If a process is not in its critical section, this should not hinder the entry of another process in its critical section. Number 3. It must not be possible for a process requiring access to a critical section to be delayed indefinitely. No deadlock or starvation. Number 4. When no process is in a critical section, any process that requires entry to its critical section must be permitted to enter without delay. Number 5. No assumptions are made about relative process speeds or number of processors. We do not assume that a certain process is faster. We do not assume that a certain process is allocated to a certain processor out of a certain number of processors, because these assumptions will make the problem more specific. We need solutions to general scenarios where any process may be fast and where any number of processors may be present. Number 6. A process remains in its critical section for a finite time only. Once a process moves into a critical section, it must move out of it too. The enforcer of mutual exclusion must ensure that a process does not starve or become deadlocked inside its critical section. Because if a process does not come out of its critical section ever, everybody else will starve. My dear students, this is the time to wreck your brains. The question is, what is the difference between the third and sixth requirement of mutual exclusion? Think, think, think. How do you satisfy the requirements of mutual exclusion? Well, there are several ways in which these requirements can be met. One approach is to leave the responsibility with the processes that wish to execute concurrently. Processes, whether they are system programs or application programs, would be required to coordinate with each other to enforce mutual exclusion with no support from the programming language or the operating system. We can refer to this as the software approach. This approach is prone to high processing overhead and bugs, so it is not used anymore. A second approach involves the use of special purpose machine instructions. We can refer to this as the hardware approach. These have the advantage of reducing overhead, but nevertheless will be shown to be unattractive as general purpose solution. A third approach is to provide some level of support within the operating system or a programming language. We will examine the last two approaches in this chapter. So come students, let's talk about the hardware support for mutual exclusion. Interrupt disabling. In a uniprocessor system, concurrent processes cannot have overlapped execution. They can only be interleaved. Furthermore, a process will continue to run until it invokes an operating system service or until it is interrupted. Therefore, to guarantee mutual exclusion, it is sufficient to prevent a process from being interrupted. Primitives are defined by the operating system kernel for disabling and enabling interrupts. A process can enforce mutual exclusion by disabling interrupts before entering critical section and enabling them after exiting from critical section. I have used a word here that I have not explained so far, and the word is primitive. A primitive is the smallest unit of processing available to a programmer of a given machine. Primitives are atomic elements. An atomic operation is a function or a sequence of instructions which cannot be interrupted. Any other process cannot access the values of variables of an atomic operation during the operation. We say an atomic operation is indivisible. When an atomic operation starts, it cannot be interrupted, so it always goes to completion. Atomic operations either execute completely or do not execute at all, but they cannot be partially executed. Let us analyze the technique of interrupt disabling. Because the critical section cannot be interrupted, mutual exclusion is guaranteed. If a process is in its critical section, it cannot be switched even if its time slot expires because the clock interrupt is disabled. If an IO transfer has completed, the operating system will not know right away because right now interrupts are disabled. The price of this approach, however, is high. The efficiency of execution is noticeably degraded because the processor is limited in its ability to interleave processes. Another problem is that This approach will not work in a multiprocessor architecture. In a multiprocessor, more than one processors are executing at the same time. This technique will disable interrupts for the processor on which a process called A is running. So on this processor, the process A cannot be switched. But if another process B starts executing on another processor and accesses the variables that make up the critical section of A, can this be stopped? No. In this case, disabled interrupts do not guarantee mutual exclusion. Special machine instructions. In a symmetric multiprocessor, several processors share access to a common main memory. At the hardware level, access to a memory location excludes any other access to that same location. This means that when a processor A generates a memory reference for location X, it places the address of location X on the address pins of the memory module, which activates location X for reading or writing. At this time, when processor A is accessing location X, any other processor cannot access location X. Designers have proposed several machine instructions that carry out two actions atomically, such as reading and writing or reading and testing of a single memory location with one instruction fetch cycle. During execution of the instruction, access to the memory location is blocked for any other instruction referencing that location. So a special machine instruction does two things, and it does them atomically. This means this instruction cannot be interrupted. This instruction uses a memory location and fetches data from this location. The memory itself provides mutual exclusion because when this instruction is accessing a location, this location becomes off limits to all other processors. Since the instruction is atomic, the location remains off limits for all processors until the instruction is complete. Two machine instructions deserve a mention here. One is called the compare and swap instruction, and the other is called the exchange instruction. The compare and swap instruction, also known as the compare and exchange instruction. This instruction takes three arguments: a memory location shown here by pointer word. This means that we are passing the address of the location to the instruction. An integer called testval and another integer called newval, and it has a return type which is also integer. It checks a memory location pointer word against a test value testval. If the memory location's current value is testval, it is replaced with newval, otherwise it is left unchanged. The old memory value is always returned. Thus, the memory location has been updated if the returned value is the same as the test value, testval. This atomic instruction therefore has two parts: a compare, which is made between a memory value, pointer word, and a test value, testval, and it is shown here in the red box. If the values are same, a swap occurs in which we assign newval to pointer word, shown here in the orange box. The entire compare and swap function is carried out atomically, that is, it cannot be interrupted. The Boolean version of compare and swap returns true if the swap occurred, false otherwise. Some version of this instruction is available on nearly all processor families: x86, IA64, Spare, IBM Z series, etc. And most operating systems use this instruction for support of concurrency. So what did we learn today? We looked in detail at all the ways processes interact. We discussed examples of deadlock, starvation, and data coherence. We realized the requirements of mutual exclusion. We delved into the hardware approach to implement mutual exclusion. So, concluding everything, again and again, I say the same things to you. Read the book and write the answers to your tasks in a Word file and submit the Word file to me when I open the assignment in Google Classroom. Write your questions on a piece of paper and keep it in front of you during the online session that would be relevant to this lecture. And if you have suggestions relevant to content or quality of this lecture, email them to me. I will see you soon. Take care. Allah Hafiz.